It's a delight to see you all here and to see at least some familiar faces, though I guess the fact that I don't see more is an indication of how long I've not been part of the academic computer science community. I'm what you might call a lapsed or reformed computer scientist. After about 20, depending on when you start counting, 25 years as a computer scientist, about 4 years ago I started to shift to become someone who works on energy. And as Alfred was saying before, I'm not a computer scientist who works on energy. I'm now an energy person who happens to dabble in computer science. And I joined here about 2.5 years ago with the job of making Google greener, more sustainable, and in the process trying to help make the rest of the world more sustainable. And what I want to talk about is some of the challenges and some of the opportunities in making an organization like Google greener. A lot of those challenges and opportunities apply to much of the rest of the world, certainly other organizations with large IT infrastructures or even small ones. And for that matter, when you start looking at the supply side of energy, then the entire world. So let me start by saying that computing technology has had an amazing track record of positive impact on society and huge transformations that we all benefit from. And that's one of the reasons I got into it, though I think when I got into computer science back in the mid-70s, I certainly didn't have a vision for what that transformation would be like. I know there were visionaries at that point talking about it. I wasn't one of them by any means. But I think the transformation has been incredible. I look at my kids and what they just take for granted and compare it to what I grew up with, and it's a huge, huge change. We could do more and make even more change, hopefully most of it positive, with more computing capabilities. But more computing typically has meant, and probably for a long time will mean, more energy. And the challenge there, from my point of view and the sort of field I've moved into, is how do we use less energy to get the same amount of work done? And how do we use greener energy? Ideally completely green, but we'll get there eventually. In the meantime, how do we make it progressively greener? And that's really what I've been focused on. So I'm going to start by talking about how to use less energy, and I'd just like to thank Luis Barroso and Urs Hotzley for much of the content. They published a paper last year, I think in IEEE Computer, that I've liberally borrowed, stolen, copied, plagiarized from. So let's start, and I'm going to focus here mostly on servers, since, as Alan put up the picture of our server farm, our data center in the Dalles. Enormous building, huge cooling towers, lots of power going in, packed full of servers. And in fact, those kinds of facilities have gotten a lot of press, and there's been a lot of what I've a few times publicly referred to as hype and hysteria around the coming sort of collapse of the industrial or modern economy, because all of the power that's being consumed by server farms around the world, and how that's going to put enormous strain on the electrical grid. I think it's mostly hype and hysteria, because in the process, all of that energy that we're consuming actually is, in many cases, enabling less energy consumption in other parts of the economy by an order of magnitude. But it's still an issue. We can't just willy-nilly use whatever energy we feel like we want to. So today, best estimates are that worldwide electricity usage of servers is around 1% of global electricity consumption. It doubled for servers from 2000 to 2005, could increase by another 40 to 75% by 2010 from there, depending a lot on how many servers, how much volume grows, as well as what the growth curve looks like for energy consumption per unit. That's where all the hype and hysteria has been. I think the interesting thing is people aren't really talking about this, which is the amount of energy used by PCs, laptops, desktops, workstations, which is likely much, much higher. The installed base for servers in 2005 was about 27 million. It's probably, I don't know, 40 or 50 now. For PCs in 2005, 870 million. It's over 1 billion today. Okay, so 1.5 orders of magnitude more. PCs use a little less power than servers typically, and their duty cycle is different. So when you factor that all in, PCs probably use something like 5 times the total amount of energy today, this year, than servers do. But people don't talk about that because it's much more diffuse and sort of scattered everywhere. And they can't point to, oh, there's that big building and there's water vapor coming out of the cooling towers and we should worry about that. But I think we need to worry about both. So if you want to use less energy, you have to be more efficient. And the first question is, how do you measure energy efficiency for computers? For the last 30 years in the PC industry, people have talked about price, they've talked about performance, they've talked about features, they've talked about price performance, right? And we've improved price performance. Moore's Law and other innovations have allowed us to improve price performance unbelievably, far more than any other technology I know of over the last 30 plus years. But people haven't really talked about energy efficiency. And I think the right metric there is to think about it as the amount of work you get done divided by the amount of energy used. In other words, how much does it cost in terms of energy to do a given amount of work? The complication there is, how do you measure work? Because what you do with a laptop might be very different from what Ed's doing with his laptop, might be very different from what the receptionist down in the lobby is doing, and very different from what my kids are doing. It's very different from what our servers are doing, which are probably different from what Wells Fargo's servers are doing. So what's the right measure for work in that process? And you can sort of think of this as a little bit like computing speed divided by power. In other words, if the thing's running at 2.7 gigahertz and it's consuming 120 watts, you can kind of, if you had those two numbers for a system, you could compare them. But that's not a great metric because computing speed is not exactly correlated to work done, as we've all learned, even though gigahertz certainly for a long time was what systems were sold on. So if you try to break it down, let's take work done divided by energy used, you break it down, well, it's really work done divided by the energy used in the chips. And that's really where the useful work gets done, in the CPU, in the memory, and on the disk, and so on. Then you want to look at, well, the chips are using energy, but not all the energy that goes into a server, or for that matter into a PC, actually makes it to the chips. So you got to divide that by the energy provided to the computer. And then when you talk about a facility like a data center, or for that matter a building like this that's full of workstations and so on, look at the energy provided to the computers divided by the energy entering the building, because there's building overhead. So in the building and in the computer, there's overhead, waste. There are power supplies here that waste significant amounts of the energy that comes into them. There's cooling overhead, there's overhead to provide backup power and so on. So all of those things reduce your overall efficiency. And if you just focus on the chips, you could say, well, wow, I've got one of the most efficient CPUs in the world. That's great. But if you then put it in a system that throws away half of the energy coming out of the wall and put that in a facility that has 100% overhead, so it's 50% efficient, your overall system is pretty bad. So this is computing efficiency, really what computer scientists tend to focus on. This is the computer, and this is the data center. And in the data center world, since people like to be ornery and confuse things, they talk about PUE, which I think stands for power usage effectiveness, which is 1 over the efficiency, just to complicate matters. But it gives you a direct measure of facility overhead. If the PUE is 1.5, that says for every 1 watt going to the computers in the facility, half a watt goes to facility overhead, okay, which would translate to an efficiency of 2/3. Okay, so where are the opportunities in energy efficiency? Well, one is in data centers, and this is an area where you look at our facility in the Dalles, and we're not going to give you a lot of details about it, though over time, I think over the next few months and couple of years, we will be more and more open about it. But there's enormous opportunity to make those facilities more efficient. Lawrence Berkeley Labs did a survey last year, showed an average PUE of 1.83. So for every watt going to the computers across the data centers they surveyed, for every watt going to the computers, 0.83 watts, or 83% of the additional energy went to cooling, backup power, losses in power distribution around the facility, et cetera, lighting. The lighting's usually, these days, in energy-dense facilities, a pretty small part of it. That's crazy. That ignores the additional overhead inside the computers. But this is the way we've been building facilities for the last 20, 30 years because energy was cheap and we didn't have to worry about it, okay? But that's beginning to change. Our facilities, I won't give you an exact number, but they're much, much more efficient than this. And one of the ways we get that is rather than using mechanical chillers, the kinds of package units, cooling units that you'd find on the roof of a building like this typically or something, where you're running compressors to move the heat out of the building. Instead, we rely very heavily on evaporative cooling, which from an energy point of view for evacuating heat is much, much more efficient. But to do that and do that well and do it most of the year, there are a lot of things you have to design pretty carefully. And this is stuff that I never learned anything about in my 25 years as a computer scientist. This is about mechanical engineering, electromechanical, electrical engineering, and so on, at a scale that I think, in fact, when I think about, when I was in school back in the 70s, there were, in electrical engineering departments, there were still people who did, power engineering. But those parts of the departments were beginning to shrink. Okay. I think this is an area where as we start to build very large energy-intensive facilities, and as we start to think about, from the point of view of greening the energy supply, transforming our energy infrastructure, that's an area that's going to need to expand again. And we're going to need people who are trained in it and can do research in it and so on. So I think we're seeing some cycles there. The other issue that is huge is data centers that are underused. So if you've got a data center that's been built out to be able to provide, say, 10 megawatts of power to equipment in it, but you've only populated it with 2 megawatts worth of equipment, you've probably got backup power facilities, oversized equipment of various sorts in power distribution, oversized cooling that is now running at very light load, and as a result, all of that is running typically inefficiently. And so you're wasting much more than you would if you were running, say, at full load. In addition, and I think Luis had a paper where he talked about, if you look at the provisioning of capacity at various levels of a facility, from the rack level to the row level to a cluster level to an entire building, typically what you find is that there's a lot of stranded capacity. That when people build facilities, they look at what's the nameplate rating of all the stuff at a given level, and then they add it up and they keep aggregating. And they build out each level to be able to handle the maximum peak nameplate of everything that it feeds. And you never get even close to that. And the result is you're building the cooling and the power distribution and the backup power to support much more than you actually can put in there. That leads to serious inefficiencies. So understanding what the actual loads are in terms of power, not computing loads, but power under real use is important if you actually want to build a facility and have it be efficient. So this is an area where we've been doing a lot. I think there are opportunities here for research. There's certainly opportunities for students who are trained in the right kinds of things to come in and help us and help others. And there's a huge opportunity for the industry to reduce the power consumed by data centers by 30, 40, 50% over the next 5 years by better design of new facilities and simple changes, relatively simple changes to existing ones. The second important area is in the computers themselves. And one of the big opportunities there is in the power conversion devices, the AC to DC power supply and the DC to DC voltage regulators on the motherboards in the server, or for that matter, in a desktop. Laptops do better, certainly on this stuff, than desktops or many servers, simply because of battery life and because of the small form factor. If they don't make those things efficient, they're going to get too hot, and you're not going to be happy with them on your lap, and the battery won't last very long. But in a typical server, most power supplies lose about 25% of the energy coming into them to heat. So 75% of what comes from the wall or from the power distribution into the rack makes it through the power supply to the motherboard. And we know how to do much, much better. The technology's there. In fact, our power supplies are about 92 to 94% efficient in our servers. And we're not doing that, certainly we've got altruistic motives in part, but we're saving money in the process. And I think there's an opportunity, especially with the move toward digital power supplies and digital power conversion. There's an opportunity, in fact, to make those kinds of power conversion devices much more efficient without having to spend extra money on them. Today, they cost a little extra to make them more efficient. But that, certainly for servers, that cost, you get that extra payment up front back in reduced operating costs very, very quickly. For PCs, it takes a little bit longer, maybe 2 or 3 years. For servers, it's going to be months. But I think there's an opportunity to reduce that cost premium enormously. The voltage regulators, DC to DC converters, lose another 25% or more in a typical desktop. So if you look at a desktop, what you'll find is you've got power coming from the wall, and typically half of that energy coming from the wall is thrown away as heat before it even gets to the chips. I mean, the chips turn it all into heat too, but they actually do some useful computing in the process. From an energy point of view, if I weren't a computer scientist, I'd look at a desktop or a computer and say, well, that's a space heater, right? There's something else going on in there, but it's basically just a heater. It's taking energy, from the electric lines, and it's turning into heat. That's what it does. But the chips at least do some useful computation. Maybe they could do it more efficiently. But the power supply, the DC to DC converters, there's no useful computation going on there. It's just voltage and current transformations. And you'd like those to be a lot more efficient. Obviously, there are cost trade-offs, but you can make them much more efficient. So one of the things that we did last year was we started an initiative called the Climate Savers Computing Initiative, which the focus is basically to drive much higher efficiency through IT equipment. And this is mostly not a research effort today. It's an effort to set some standards on efficiency targets, and also then to get purchasers to sign up and to pledge to buy high efficiency equipment. Most purchasers today look at, well, this one's cheaper, I'll buy that. And I think that's true for institutions as well as individuals. One of the things we're trying to do here is drive demand so that as the demand grows for high efficiency equipment, the price premium that's there today will go down because it's mostly a volume manufacturing issue, not a technology issue. And I know that a few universities have pledged to basically to purchase high efficiency equipment when they're buying PCs, et cetera. If yours hasn't, here's the shameless plug, please join. Encourage your institution to join. I think there's an opportunity to really transform the market for IT equipment, and particularly for power supplies and DC to DC converters, and drive out inefficient equipment from that market. But to do that, we need to drive demand up quickly. Okay. Then the third thing is the actual computers. And today, computers, especially servers, have poor energy efficiency in their most common usage range. So they may be designed to be relatively energy efficient when they're completely idle, okay, or when they're 100% utilized. But most systems don't spend very much time in either of those regimes, especially servers. Laptops and desktops spend a lot of time just idle. But servers don't. And this is a real problem. So I'm going to talk a little bit more about this. And in fact, this is a distribution of CPU activity in a number of our servers over a 6-month period. This is 100% utilized. This is completely idle. And what you see is that they aren't running full blast. They're hardly ever running full blast. That they spend most of their time from 20 to 45 or so % utilized. And a moderate amount, though not a ton, down at the very low end. Yeah, question?
Is this an average over a set of computers or a snapshot of one?
I believe this is a snapshot of data from a bunch of systems, not just one. So it's a range of workloads. But I think if you look for most of our workloads, and I suspect for most server workloads, if you look just at a single computer, you'll see a very similar picture. Okay. So they aren't running full blast, and they mostly aren't idle, but they are running something all the time, or most of the time. So from an energy efficiency point of view, you could ask, well, what's if I run a workload to run them, sort of flat out, what's my efficiency? What's my work done divided by energy used? So if I run some spec benchmark and just crank it as hard as I can and look at how many spec marks I get in an hour and how much energy did I use, that's a measure of efficiency. But for real systems, that's not very interesting because that's not how they operate. So you need a workload that somehow captures this, and you need systems that are energy efficient in this regime, not just up here and down here. Yeah?
Doesn't that mean you just need fewer computers, that your servers are not efficient in not...
So the question was, doesn't mean we just need fewer computers. and that our servers aren't efficient? And I think the answer to that is, unfortunately, no. Okay? There are times when, because of when you have large-scale cluster-based services, first, the overall, you need enough capacity to be able to handle your maximum load with reasonable latency for the users. A lot depends on your workload. If you're running a non-interactive service, if you're, have a scientific computing data center, well, in fact, you can probably arrange so that you've got, and you probably in fact have very quickly after you install a new supercomputer, that you're up in this range. Because you've got plenty of demand and you're running what are more or less batch jobs in some sense, and people are just cranking it as hard as they can. But when you're running interactive real-time services, you need enough capacity to handle your peak load. And if you try to run, and this is where my queuing theory is old and rusty, but if you try to run up in this regime, you're going to find latencies going through the roof. Okay? So you need to be no more than sort of up here in terms of utilization before you start to see major increases in latency. And certainly for Google, we have made latency and low latency a key design goal for our systems, right? And when you then look at, well, okay, if this is our design goal sort of at peak to avoid large latency, this is where you're going to be most of the time because you're mostly not for the whole system running at peak. Okay, Mendel.
Yeah, I thought, looking at that at a high level, I would say your load balancer needs work. Right? How much of that is that, some better load balancing technology, you can still keep your latency requirements and stuff, yet drive that.
Okay, so the question was, this looks like you just got a crappy load balancer, which I don't think is true. So let me go a couple more slides and maybe we'll come back to that. But one of the messages here, I think, is that a data center is not the same thing as a laptop. The workloads are very different. The way you manage it is very different. And obviously, the energy demands there are a little different than certainly from one of these. Okay, but this really gets to Mendel's question, which is if you think about a well-designed, large-scale internet, huge cluster service, you want high performance, you want low latency, you want high availability. That requires load balancing. It also requires wide data distribution. These aren't just computations. These are computations involving data. And if the data isn't where the computation is running, you got to move it. That's going to add latency. So you need services that have data distributed around and can run the computations in appropriate places. And what that means is because of that data distribution, but because of managing that, what is typically then replicated data, you actually don't have much in the way of useful idle intervals. Certainly, a system might be idle for a brief period, but it's not going to be idle for 5 minutes or 15 minutes where, like with a laptop or desktop, you might say, let's put it to sleep. Okay? And you have lots of low activity intervals. And I think today, this is fundamental to the way we're building these kinds of services, and for that matter, I think to the way many people, most people are building these kinds of large-scale internet services. It's not fundamental the way every data center-based, sort of back-end business application or service is running, but for these kinds of services with replicated data, high availability, low latency, high performance requirements, I think that this really is fundamental. And I think there's an interesting question of how could you design those services? I was talking to Fred about this a little bit last night. How could you design those services, those kinds of replicated services, so that, in fact, when load on the overall cluster is low, you actually could avoid those low activity intervals on most of the machines. Today, they're required, if you have something where you, so take GFS, replicas are on multiple machines, you've got reads load balanced very nicely, and you could choose to say, well, if the cluster's at 10% utilization, we'll concentrate all of those reads on 20% of the cluster. And those machines will be 50% utilized. And the others won't see any reads at all. So you can say, well, now we could shut them down or put them in some very low power state. The problem is if there are any writes, you need to reach them all. And if anything breaks, the whole cluster is involved in rebuilding replicas. And the result of that is there's low activity on every machine. So could we design those services, in fact, to be able to put, so that the machines that we choose to direct load away from could actually go into a very, very low power state. That's one possible solution to these problems. Okay? I don't know how to do that very well today. And I think if somebody does, that would be great. Yeah?
Yeah, I just want to ask a quick question about the big thrust behind the server consolidation and virtualization. It seemed like the graph you showed on the previous slide, where most of the machines were running at 20% or whatnot, is
Well,
exact
let's say the average is probably, you know, I don't know, 30, 35%
right
on this. Yep.
But the key is this exact motivation where you can run 2 or 3 virtual machines on a single physical machine and then shut down some of the other ones.
Right. So we do run several services on any given machine. We don't use, you know, say VMware or other virtualization software like that, but we're effectively getting that kind of effect. The issue really comes to, if you shut those machines down, they're now not participating in the replication service. So changes happen to the data. When you need to bring them back up, the question is, how do you bring them up to date? How long does it take? What's the latency to actually reintegrate them into that replication service? So they're not simply machines that you can say, I'm just going to shut them down and nothing's going to happen that affects them. Okay, number one. Number two, there is business value in having machines that are idle and ready to take on load very, very quickly. So the latency to bring up a machine and reintegrate it into the cluster of services is a key issue. Okay, but it's definitely something that you know, increasing, you know, if we could get our average utilization, I mean, I don't think we'd want to go much above 50% because then we'd start to see latency go up because of queuing. But increasing average utilization to 45, 50% would be a great thing. But it's not a simple thing. Yeah.
So, Bill, there's something you can dismiss till later if it makes sense, but there are a lot of technologies that are about energy scavenging that have nothing to do with making computers more efficient. To give you an example, you can scavenge vibration at certain frequencies up to about 60% of energy value. So there's this trade-off in your green program between, you know, innovation in energy scavenging versus a potentially higher cost of configuration and machine configuration and design. Do you pay attention to that, or is it outside of your realm right now?
So the question was about energy scavenging and whether you're scavenging vibration or waste heat or whatever, turning that back into useful energy. You can scavenge some of that wasted energy, whether it's mechanical energy or thermal. There are limits to what you can get there, and all of the solutions I know there don't get you very much back and cost a lot. So if you've got finite budget and people to figure out ways to do it better, today that's not where I would put my money.
So it is a trade-off.
It is a trade-off. And you know, there's still opportunities, lots of opportunities in our systems and in other people's systems to do better. That's one avenue. At the moment, I don't see, I think that's one that needs a lot of really basic research before it shows real promise to be deployed on any significant scale.
Another one that doesn't need so much basic research, if you talk to people, there's some here, that deal with sensor networks and cost of data transmission. One of the ways to address that is to use good old-fashioned mathematics technology like Alan Eustace was telling us about to manage the value of data in the network in a way that's independent of the physical infrastructure. You must pay attention to that.
Right, so question of value of data versus physical infrastructure, where the data is located, and trying to manage that, yes. I think one of the things you could imagine doing is saying, you know what, some data is lower value or less frequently accessed, so we'll accept a higher latency to get at it sometimes. You know, we'll spin down disks and do other things that mean that sometimes we're going to take a latency hit. That might be okay for some data, but you have to be very careful with the user experience. This is one of the things I learned at Akamai, that if you look at the latency curve that people experience, the tail of that curve really matters. And even if people experience a very long latency quite rarely, it colors their perception of the overall service. And inconsistent access times or response times really matter in terms of user experience. So it's definitely something we think about, but it's something you got to be very careful about. Okay, so let me move ahead a little bit. But one of the things it says is that today, given the way our systems and a lot of other people's systems are designed, strategies where you put systems to sleep or power them down for servers aren't necessarily going to work very well. It's not easy to make those work well. And if you focus on energy efficiency at peak performance, which I think SPEC is beginning to, where they're looking at SPECPower, for example, that's not where systems run. In fact, they're never really going to run flat out if you care about latency. So that's the wrong thing to really be focused on. Now, an interesting thing is if you look at power, the question is power efficiency versus activity level. Okay, so a typical server, this is somewhat fudge data. This isn't exactly the real data, but it's pretty much what we've seen looking at our systems and other people's systems. When a system's running at 0% load, just idle, it might be using about 50% of the power that it uses when it's flat out at 100%. Okay? Now, down here, notice that the efficiency, if we graph efficiency, not power, efficiency is 0 because you're not getting any work done. And over here, if we normalize it, efficiency is 1. Okay? But in between, it drops in essentially a quadratic curve. Okay? So when you look at, say, 1/3 of peak utilization, which is a likely activity point for a lot of systems a lot of the time, you actually drop your efficiency by half. So if you measure efficiency here, and that's what you care about, and you optimize for that, you're not actually running there a lot of the time. Your efficiency is much worse in terms of work done divided by energy used at the points where you typically run. Mendel.
Isn't that red line just solely set by the power management strategies you're using on the server? And it seems like you would argue that better power management would cause it to approach the green line.
Isn't this red line set by the, so this line is the power used at different activity levels. Right. It's nothing to do with power management. Say if we're 30% utilization, this is how much power the system uses.
No,
okay.
That's a function of what the power management strategy.
It is a function, but I'm talking about, it is a function of power management strategies, but if you look at the power management capabilities in the hardware and the software on machines today and ones that I know of coming out, this is the kind of curve you're going to see. Okay, and if you disagree, I think we should talk about it later. Okay, Intel has some very interesting roadmaps, and I'll get to that because Intel is only a small piece of the story. Okay, so if you look at this from SPECPower, you see exactly this. If you run at 100%, you know, you get this is and look at the average power. This is your this is the power that's used for these various target loads, okay? And this is the power efficiency, work done divided by the energy used. And when you look down here at, say, 30% target load, you're at about half of the efficiency, 737 divided by 1610, a little less than half of the efficiency when you're running at peak load. Okay? So that, I think, I mean, this is data from real systems running real applications. And I think if you replicate this on other servers, you're going to find most likely very similar data. But there may be ways that you can change it. And I think that one of the points here is we need to change this. Okay? So the idea that what we'd like to see in our systems and in other people's systems is systems where the energy you use is proportional to the amount of computing you get done. So if you're not doing any work, you don't consume any power. That would be ideal, or very, very little. If you're doing some work, you consume some, and if you're doing a lot of work, you consume a lot of power. Okay? And then we wouldn't need, I mean, if you had systems that did this, you wouldn't need power management software. You wouldn't need to have the system go to sleep and sometimes fail to wake up, or sometimes fail to go to sleep because drivers are hanging on to resources and the system can't put it to sleep. You know, the system would it would just use less power when it's doing less work. So if your system's idle, you know, fairly quickly it goes down to using very little energy. So the question is, what's keeping us from achieving that? So this really gets to your point about Intel having all these wonderful roadmaps. Intel and AMD actually have done a lot to make CPUs much more energy proportional over the last number of years. Both energy efficient, going to multi-core architectures, but also energy proportional. Multiple power domains on the chip where you shut things down when they're not in use, for example. So if you look at the different components of a system and the power they consume at different activity levels, this is the amount of power, and this is as a percentage of peak, amount of power that the CPU consumes when you're running flat out. It's almost half of the power consumed by the system. This is DRAM, this is disk, that's other stuff, okay? As you drop the activity level, the CPU drops a lot. The other components don't drop as much. So even if you got the CPU to 0, even if you made this a straight line, okay, you'd still have pretty significant amounts of power being consumed at low activity levels by the other components. And if you look at this now as a percentage of the total, you can see that much more dramatically. The CPU drops from 50% to around 30% of the total. The others become a much larger fraction. So the CPU, especially at low activity levels, doesn't dominate the whole system. It's much more balanced among the different components. And really, what's going on there is the CPUs are fairly somewhat energy proportional, not perfect yet. But the rest of the system is not. The amount of energy consumed by DRAM, by disk, by the other stuff doesn't change that much at low levels. So why do CPUs manage to do this? Well, they've got a very wide dynamic range. So an idle CPU consumes less than 30% of peak power. Other components, it's 50, 75, 85% of peak power when they're idle. So when they're idle, they don't throttle back on energy consumption very much. And furthermore, for the very low power modes, CPUs have what you might think of as active low power modes. By scaling voltage and frequency with CPUs, you can still execute instructions just more slowly, but that's okay. Whereas other components, the low power modes are mostly inactive. So you trigger those only when there's zero activity. You put the system to sleep. You have a very small amount of power. You spin down the disk, you turn off the network interface, you have a small amount of power going to maintain the contents of memory. But you can't actually do any work in that state. So what we need is active low power modes for other components. Or if you're going to have inactive low power modes, you need very, very low latency to wake them up, okay, which we don't have today. Yeah?
Do you see these trends changing for disk as we transition to flash storage?
Flash storage has very different characteristics than, the question was, do we see this changing as we transition to flash or solid state disks? Flash has very different characteristics here. And so that, and I think better in a lot of ways from an energy point of view. If you do put them to sleep, well, first of all, they're non-volatile. So you can reduce power consumption, and the latency to get them going again is very, very low. Whereas a disk, if you spin it down, there's significant latency to spin it back up. So yes, I think there is a potential for big improvement there. Now, when we will move to having no disks and all solid state, I hesitate to go there. And I don't want to try to predict that. Yeah.
If you looked at the amount of energy required to execute a user transaction, how has that varied over the last few years? And this gives rise to, are there algorithmic issues and programming language issues that arise in terms of how you implement the activities that you're doing to minimize energy consumption?
So the question was, if we look at the energy used to execute a typical user transaction, how has that changed over the years? And how much is that affected by software, the programming languages, the tools, the algorithms, et cetera?
And the volume of data.
And volume of data. Right.
Amount of data.
So the data has gone up enormously, as Alan was talking about, especially if you start looking at things like video. At the same time, the density of disks has gone up enormously. So I think that the energy used to execute a typical user transaction has probably improved in the last few years. I think there was a period when it wasn't improving much, partly because the CPUs were really pretty much flat in terms of performance per watt or efficiency. But in the last few years, they actually have gotten significantly better. I think that there's still enormous room for improvement by paying attention to these kinds of issues in the hardware. Software makes a huge difference. Okay, so if you write more efficient software so that you can actually get more done with the same hardware and the same energy consumption, that's probably in some ways the easiest thing to do. well, I don't know if it's necessarily the easiest. Software engineers would probably say, you're out of your mind. It's not an easy thing. Actually, getting higher utilization and tuning the software isn't necessarily easy, but there is an opportunity there. It's something that we pay a lot of attention to. It's ongoing. You can't think you've fixed it and then you're done, because people are writing new software and modifying existing software all the time. But that is clearly a huge piece of it. Efficiency of the software in using those resources translates very directly into efficiency in energy consumption. So teaching people, for example, you guys being out there educating the folks we're going to hire, teaching them about efficiency and how to measure the efficiency of their programs, and beginning to get them to think about not just computational efficiency, but energy efficiency. And teaching them about algorithms and how to design algorithms that are more efficient really, really does matter, especially when you start talking at scale like this. If you're writing an application for a PC, maybe the PC is more than fast enough to just do what you need to do and you don't have to think very hard about it. But if you're writing something that's going to run on thousands of machines, well, if you can run it on half as many machines, you can either save money on the infrastructure or get twice as much done. And for a business like us, either of those, or some combination of those really matters.
The last question brings up an important connection to your question about latency, because you were talking about time latency for a user at the end, but there's semantic latency. The old algorithms guys know that if your algorithm isn't correct, you're likely to be able to compute the answer in constant time. It's a little joke, but the point is that sometime you're going to have to couple semantic latency in this equation too, because I want an answer that's good enough in the energy trade-off versus the decoupling that you're speaking of now.
Right. So the question was about user latency versus what you might think of as semantic latency, which is there a notion of good enough for an answer? And could you say stop after some amount of time or some amount of energy and say, no, this is good enough, or I've spent my time or energy budget, I'm going to give you the answer I've got. And that's absolutely something that for a lot of services really can matter. For email, when you want to click on an email and see it, well, I can only give you half the words. But I ran out of energy, I'm sorry. That doesn't work, okay? But for an internet search, there is no single right answer. You just want a really good answer. And so we need to make sure it's good enough.
Part of it relies on an objective measure of resolution of answers. So if you can, for example, map data is easy to imagine resolution. Email opening and speed is not so easy. I don't want every second.
Right. So different services, I think you're absolutely right, that there may be useful notions of resolution or good enough for some and maybe not for others. Okay. So I just want to draw a quick analogy, and then I want to move for the last few minutes to talk about the energy supply side, not just the demand side. Okay. You look at a person and a typical desktop machine, and they're kind of similar in terms of average power, around 120 watts. Okay. You look at the performance or energy, power consumption versus activity level for a PC, and that's kind of what the curve looks like. 2x difference from idle to peak. You look at a person, and this is Lance Armstrong's tour stage, okay? 1,200 watts here, and resting 60 watts, okay? So a factor of 20, not 2. Order of magnitude difference in energy proportionality, okay? And actually, Louise has a really fun graph that shows a whole range of activities that people engage in that really span this range and show you a much more linear curve here. Okay. So there are lots of examples of devices, natural and otherwise, in the world that have this kind of dynamic range. We're not building computers that way. And I think the simple answer is we never needed to. It wasn't that important. I think it's becoming important. So what if we could build machines that had an activity range, very wide dynamic range here in energy? That's something that I think we really need to work on. So if you had a better server, and that's what the power curve looked like, you'd see an efficiency curve that looked more like that. And in this range, a third of peak, power efficiency is above 80% of what the power efficiency is at peak. That's pretty good. Okay. So that's, I think, what we need to strive for as much as possible. Okay, so let's talk about the supply side, which in fact is where I spend most of my time. I kibitz and talk to Luis and others who are working on facility design and system design about the demand side, if you will. But I spend most of my time here. In fact, on how to use greener energy. And just to give you a sense of what the problem is that we're facing, in the US in 2004, and the data since then is pretty similar, coal was responsible for about half of the electricity generation. And coal, from a greenhouse gas, and in fact most other pollutants perspective, is the worst that we've got. Natural gas was a little under 20, oil was very small. Back in the 70s, oil was pretty big for electricity. We pretty much almost completely stopped using it. Nuclear is about 20, hydro, 6.5, renewables, 2.3, and then there's a little bit of other stuff, okay? So,
yeah, isn't hydro renewable?
well, it depends on who you talk to. Most people would say it's renewable as long as you have good rainfall patterns. It does have big ecosystem impacts. Okay, though the truth is, I think any large-scale energy generation, whether it's solar, wind, or something else, there will be some impacts. Okay, but I think the real issue with hydro is if we want to think about how we replace all of these polluting sources, which account for almost 3/4 of our electricity generation today, with things that don't pollute or don't pollute anywhere near as much, we don't really have good opportunities in the US or for that matter around the world to expand hydro. In fact, the hydro we've got may well decrease in its output if we continue to see changes in rainfall patterns and particularly snow patterns that people expect. Okay, so we could debate whether it's renewable, and some environmentalists would say, don't call it renewable because it has such huge impacts on ecosystems. But it really doesn't matter because that's not where there's room for growth. But it gets worse. And this is part of why I reformed a few years ago and became an energy person, which is I'd spent a lot of time thinking about what I want to do for the next 20 years of my career and where was there an opportunity and a need for enormous impact. And as I thought about the problems we're facing in energy and in climate, this is where I started to get really scared and decided to see if I could try to do something about it instead of just being scared. So coal is responsible for about half of the electricity, but about 3/4 of the greenhouse gases. So we can do all sorts of things around renewables, but the message from this is that until they can compete with coal, we're not going to solve the problem. Okay? And in each of the last 4 years, China added more coal-fired power plants than the entire electric capacity of Spain. And as far as we can tell for the foreseeable future, that's what they're going to do. So until we can come up with solutions that make it so that China doesn't feel the need to do this, and that they can still continue to grow their economy but not do it on the backs of coal, I think that we're in trouble. And the Western world, the current developed world, we build our economies on coal and other non-renewable, non-sustainable, very polluting sources. But we need to find a way to transition our energy infrastructure and find a way to help the developing world grow and grow their economies, but in a different way than we did. And the US and Europe, sad to say, are also adding coal. Okay? And there are reasons. One, it's cheap. Two, you can get reliable, what people call baseload power, right? That's there all the time, or most of the time. You obviously have maintenance outages and so on. Whereas solar and wind are intermittent. Sun shines during the day, many days, not all days. The wind blows when it blows, but certainly not all the time. Okay? So you can't get constant, reliable, firm power out of those sources. But the other issue today, and this is really, I think, a key issue in the problem, is that from a cost point of view, renewables can't compete with coal at all. In China, cheap pulverized coal is somewhere between 2 and 6 cents a kilowatt hour. In the US, it's a little more expensive, maybe 3 to 7. If you do gasification with combined cycle, it's somewhat more expensive, but most people aren't doing this. There are very few of these plants because they're expensive, and they're somewhat cleaner, but not a lot. Natural gas is, 6 to 10, depends on very volatile with the price of natural gas. Coal, if you do gasification and do carbon capture and sequestration, which basically isn't being done at scale and commercially today, that's going to bump the price up even more. Nuclear and wind are here, still more expensive than coal. Wind, sort of competes economically with nuclear, but it's intermittent. Nuclear is a baseload source. So the value of nuclear is much higher than of wind to a utility. And then when you start to look at geothermal, solar thermal, PV, that's actually a very misleading bar for PV because the ceiling doesn't go high enough. It's probably more like 25 to 35 cents a kilowatt hour, okay? They're just completely out of range.
What's the acronym?
Photovoltaic, I'm sorry. Okay, solar photovoltaic. So the solar panels that, when people think solar, that's what they think of. Solar thermal, this is what people sometimes call concentrating solar power. It's Archimedes plus James Watt. You and a little bit of high-tech materials here and there. You concentrate the light. I don't know, you may have heard the story of Archimedes with, the guys with the bronze shields reflecting the light onto a, attacking warship, and it burst into flames. And there have actually been some interesting experiments trying to replicate that. This is a little less aggressive, shall we say, but the idea is to concentrate sunlight onto some kind of receiver. And then the most common thing that people do there is that they heat something up, it's either water or something else that then you use through heat transfer to heat water and make steam, and then drive a steam turbine. So you got Archimedes, you got James Watt, piece of cake. But it's expensive, okay? It's closer than solar photovoltaic. There's a pretty clear cost decline curve that solar, PV, and wind are on. The question is, when are they really going to be cost competitive with coal? And so what are some of the challenges and opportunities here? Well, one is to drive down the cost. And we started a major initiative last fall called RE less than C. It breaks every HTML page if you just type it in there, unfortunately. And you might think as an internet company that we would have thought of that before we came up with that acronym, but it stands for Renewable Electricity Cheaper Than Coal. So the goal of the initiative is to drive innovation to drive down the cost of renewables and do that quickly. And the reason we thought that was something that we wanted to do and that we couldn't just leave to the marketplace, and we don't expect we're going to do it ourselves, but the capital markets today, and for that matter, the government funding of research, is the focus is on getting to what people call grid parity, which really means at some level beating the price of natural gas. And as I showed in that first slide on this, that'll solve maybe a quarter of our greenhouse gas problem from electricity, but it leaves 3/4 of the problem completely unaddressed. So we need to set a target that actually will solve the problem. And our hope is that lots of others will focus on that as well. Solar thermal, CSP, and what people call engineered or enhanced geothermal systems are probably the least mature of the technologies that could be done at utility scale that could really power our economy. And the nice thing about that is that those are, as a result, probably the areas where there's the most opportunity to drive costs down quickly because they're still at the very steep part of the cost decline curve that we could get on through innovation. Wind is much more mature. There's still opportunities there. But they've been, I think at some level they've hit diminishing returns in certainly current technologies. The other challenge, and there's clearly an opportunity, but there's a huge challenge here, which is how to scale. Renewables are 2% in the US, or a little more than 2%. That order of magnitude worldwide. How do we scale that to 50 or 80% over the next 30 years? If you start looking at the amount of investment required and just the amount of steel and et cetera, the sort of level of industrial stuff that has to happen, it's enormous. And how do we do that? Will the capital markets and the sort of natural free markets do that on their own? And my guess is not fast enough, certainly, to deal with the climate problem. And if not, then what can we do from a government policy, market incentive point of view, research, investment, et cetera, to try to accelerate that? Because I don't think we've ever, there's anything else where we've scaled as fast as we need to, certainly not sustained for that long. The transformation of our industrial economy in World War II, where we basically just shifted to building tanks and planes and so on, maybe is the closest analogy. We didn't do that for 30 years. Storage is another key issue, since the major renewables, solar and wind, are intermittent. Geothermal has a nice property that actually it's just there. So that's one of the things that makes it very attractive. But if you're going to have intermittent renewables, you need to provide baseload power. People need power when they need it. You better have some way of dealing with that. And then another issue, and this is where I think actually computer science can start to play an interesting role, is that the grid itself, first of all, from just a power engineering point of view, it's ancient. Okay, we're building the grid with technology that's 80, 100 years old. So there's an opportunity there to be much smarter in terms of the sensors and the control of the grid. But then I think there's a very disruptive idea, which is to start to think about the way the grid is operated today. People dispatch the sources. Dispatching means basically at any point in time, the loads and the sources need to match. If you produce more power than is actually being consumed, then you get frequency and voltage fluctuations, other issues. If you produce less than is being consumed, you get brownouts and other problems. So they need to be matched very closely. And that's what the grid operators do. They do that today by having the power plants ramp up and down their output to keep it matched to the load. But what if we were to start thinking about dispatching the loads, not just the sources? Now, obviously, there's some loads you can't do that with. If I'm sitting here working and I need a light or this projector needs to be on, I can't have PG&E saying, you know what, dim the projector or turn it off for a couple minutes. That would make for very weird life. But there are a lot of things that actually you can choose when to consume the power and still get the work done that you need to get done. So take something like a plug-in hybrid car or an electric car. Plug-in hybrids are probably better for this, but you could choose when to charge. You don't have to have them just charge when you plug them in. They could charge, say, when the wind is blowing and you're actually producing wind power. Or cooling, air conditioning. Well, if you've got a cooling unit, it's making cold air and blowing it through the building. You need to do that when you need it. You don't want the temperature in the building fluctuating up and down wildly. But suppose you put a buffer in between and have the cooling unit make ice, or in some other way make cold, that you then use when you need it to actually make cold air. You can choose then when to make the cold and start dispatching those loads. And lots of major appliances, same thing, right? Imagine if, in the evening, I'd be happy to put the dishes in the dishwasher, close it, hit a button, and it'll decide at some point during the night when to run. I don't care. Okay. But today, I hit the button, it runs. If I want to run at 3 a.m., I got to set an alarm and get up, and I'm not doing that. My kids are too old. I don't need to do that anymore. Okay. So this is an idea that then becomes a massive information gathering and then control problem. But there's the opportunity with many of these devices to control it on much finer timescales than people can with the grid today, which actually I think leads for an opportunity to make the grid much more stable. Okay, so what are we doing? Let me just flip through this. I'm not going to talk about it. I'd be happy to talk one-on-one or in small groups. We're doing R&D, we're doing some investments. We expect to do some academic research awards and invest in renewable energy projects. We're becoming active on energy policy, and we'll have, I expect, a lot more to announce over the next number of months. So that's it. Thank you.